In this session, I will tell you how to calculate delay in assembly language. Here is the code to blink the LED. And to blink the LED, here I am giving first the logic high to port 0. Then I am calling some delay. Then I am giving logic 0 to port 0. And then again calling delay. This code is under loop, S-jump, short jump loop. It's similar to your while one loop in C language. So it's simple LED blinking code where I am calling function or subroutine delay. So here is the code for delay subroutine. Now delay move R0 comma hash M. So whenever you want to load immediate data value to any register, you will use hash. So here M is nothing but just a value. It can be any value. Similarly is true for N. N can be any value. So this instruction will move the value M to register R0. R0, R1 are temporary registers. Similarly, the value of N will get loaded to register R1. Now this instruction, decrement jump not 0. Decrement the content of R1. If it is not 0, jump to label here. So here 1 is label pointing to the same instruction. That means till the time the content of R1 register becomes 0, it will be in a same loop. Now when the content of R1 becomes 0, now you will come down. Again there is one more DJNZ instruction, decrement jump not 0. So again the content of R0 will get decremented by 1. If it is not 0, then it will jump to here 2. Here 2 is here. It will again load the value of N to register R1. Then the R1 decrement from the value of N to 0. So ultimately, you can imagine this 3 statement as a 2 for loop. This is an inner for loop which will execute N number of times. This one is outer for loop. This will get executed M number of times. So this will give you the total iteration of M into N. Okay, let's see how much delay this delay subroutine will produce. Move R0 comma hash value. This particular instruction takes one machine cycle to execute. And we know that one machine cycle is nothing but 1.085 microsecond. Similarly, move R1. This instruction again take one machine cycle. DJNZ take two machine cycle, and RET instruction take two machine cycle. This instruction will get executed only once. This instruction will get executed M number of times since it's under R0 here. So it will get executed M number of times. This particular instruction will get executed N into M number of times. This particular instruction M number of times. RET only once. So if we multiply the number of times multiplied by the machine cycle, you will get this time. Let's take a specific case where M is 180 and N is 255. So in that case, the time to execute for first instruction would be like this, second one, this like this. So if we do the calculations, then we will find that the total delay generated by this delay subroutine is nothing but 100.19 millisecond. It's tedious to do these all calculations, So the best way is you can consider this instruction only. To execute this instruction, you require 2 multiplied by 255 multiplied by 180 91800 machine cycles, which is very large value as compared to other instruction delay. That's why if we take only this value, I will get the value 99.6 millisecond, which is very much near to my 100 millisecond value. So if you don't want to do this complete calculation, you can simply approximate the delay produced by any subroutine with this simple calculation. Now if you want a larger delay, you can add one more DJNZ condition to your delay subroutine, and in that case your approximate delay would be this much.